Hello, I'm Aidan Brown, and this is my presentation for Astro 364, Stars and Galaxies. We will be looking at the study called Investigating Gaia EDR3 Parallax Systematics using astroseismology of cool giant stars observed by Kepler, K2, and TESS. Its main focus is how we model data on spectroscopic information to find out just how far away a star is from Earth. To do this, they had to make certain assumptions and expectations of the data and the star's behavior, and compensate for any problems stemming from their methods and sources. When you look up at the sky, for the most part, we assume the bright spots seem to be stars, but in fact, some of those spots are actually planets, galaxies, or even entire clusters located billions of light years away. You can often deduce what you're looking at depending on how far it is from Earth. That's why measuring the exact distance to celestial objects is so important, and sometimes even a challenge. This was the mindset of the European Space Agency when it launched the Gaia mission 10 years ago. Data collected by the Gaia satellite gives us a look into the not-so-distant reaches of our universe, providing measurements like positions, distance, and movement on billions of stars. Now EPFL-associated researchers are using Gaia information and methods to compare results from varying sources in two ways, using parallax and astroseismology. The paper is initially motivated by two main questions. To what extent can we trust our current sources for accurate and consistent data, and how can we adjust the model for our data to get greater precision and accuracy? Let's dive into some key concepts. The researchers use parallaxes to calculate the distances to stars. This involves measuring parallax angles with the help of the satellite through the form of triangulation between Gaia's locations in space and the star in question. Despite Gaia's success, the measurement of parallax is complex, and there remains some error that must be checked and corrected in order for Gaia parallaxes to reach their full potential. This is what the researchers have been working on through calculations performed over 12,000 oscillating red giant stars. They measured Gaia's biases by comparing the parallaxes reported by the satellite with parallaxes of the same stars that they determined using astroseismology. In the same way that geologists study the Earth's structure using earthquakes, astronomers use astroseismology and specific star oscillations to gain information about physical properties. Stellar oscillations are measured as tiny variations in light and translated into waves, producing a frequency spectrum of these oscillations. The spectrum allows them to determine how far away the star is. Finally, the astronomers compared the parallaxes obtained in this process with those reported by the Gaia surveys in order to check the accuracy of the satellite's measurements. In this paper, they specifically chose to use TESS, Kepler, and K2 surveys to compare for the distances. These surveys had the most expansive networks of data on stars they chose to study, which are red supergiants. This is a graph from the paper that allows us to visualize the corrections made to the data. The parallax before, which is the top, versus after, at the bottom, shows us how much of an impact the change is made. This is most clearly shown with the change in average lines on each graph, with going from left to right is Kepler, K2, and TESS survey data. Each point corresponds to the measurement of parallax ordered with respect to their magnitude, and the color simply represents the density. In each case, the uncertainty in the data is shifted upwards, typically closer to our ideal, but with some over and under estimates. There are three main things that we can take away from the results. The models used for the corrections could still use improving, as it is not entirely clear if it was a better result produced with any of the known methods. The sources of the data used for study in the future needs to be acknowledged and considered in their models because the results vary between the sources. As such, the consistency between sources of data need improving, as there were clear inconsistencies in the measurements of the same or similar bodies. The paper brings some positive and negative points with it. It definitely challenges the trustworthiness of our sources with an in-depth analysis of parallax details and uncertainties. However, it highlights that a model made specific to the photometric information of the dataset will not be accurate for the stars outside the range of magnitude. Also, their model tended to make over and under corrections for stars whose magnitude was at the fringes of the dataset. Now we'll get into the press release. Some things it does well and some not so much. It accurately portrays the processes mentioned in the paper, explains the terms and methods that the paper neglects to mention, includes interviews and primary researchers and experts, and examines possible impacts of the paper. On the downside, it does not discuss any information on the stars in the sample and neglects to discuss the main results of the study. Overall, the press release does a good job of explaining the research and well and in depth. The paper is well structured and detailed while meeting the goal of finding out how the data measures up. However, as far as readability, the press release does a lot of heavy lifting for the paper. Most of the understanding and concepts from earlier were not explained in the paper, but were in the press release.